All right, welcome in everybody. Thank you for joining us on your lunch break here in this fine Wednesday. We are excited to get started, but we're going to give people a few minutes to just get settled, let some stragglers in here, and then we'll kick it over to Robbie to get started. So give us about 10, 15 seconds. All right, Robbie, I think we got a good number in here, and we'll let the stragglers come in as you keep going. Kick us off whenever you're ready, sir.
Okay. Hello, everyone, and thank you for joining us today. Today, we're going to talk about a distinction that sounds simple, but it has major implications on how we design, assess, fund, and operate facilities and regions of the United States that are susceptible to hurricanes and tornadoes. That distinction is the difference between a facility that is built to survive and a facility that is built to last. Most buildings in the United States are designed to meet the International Building Code, and that's a reasonable starting point. But the code is primarily a life safety document. It's not intended to guarantee business continuity, emergency response continuity, utility continuity, or immediate recovery after a major event. The question for today is not whether code compliance matters, it absolutely does. The question is whether code compliance is enough for facilities that communities, agencies, and organizations rely on when conditions are at their worst. We will wait till the end of the presentation to address Q&A, but if you have any questions during the presentation, please feel free to type in the Q&A section. Before we get started, I'm going to briefly introduce myself. My name is Robbie Vogel. I am a professional engineer in 11 states, and I serve as the Director of Structural Engineering at WGI. My work focuses on structural engineering and assessments, ICC 500 storm shelter, and FEMA P361 safe rooms, both new design and peer reviews, resilience evaluations, and helping owners understand how structural decisions affect the long-term performance of their facilities. This topic is especially important to me because structural engineering is often perceived as being limited to whether a building stands or doesn't stand. I mean, in practical applications, we know what failure looks like as a structural engineer. But in practice, especially for critical or operationally important facilities, that is only a part of the question. The more important question is often whether the building can still perform as designed when conditions are at their worst. For those less familiar with WGI, we're a multidisciplinary firm with offices across the country, including major markets in Florida, Texas, and North Carolina, and other regions that are directly exposed to hurricane, tornado, flooding, and extreme wind hazards. The geographic footprint is important to today's conversation. Many of the markets we serve are no longer dealing with a single and isolated wind hazard. Florida and the Mid-Atlantic are not only coastal hurricane market regions. Texas is not only a tornado or straight line wind market. Increasingly, owners are facing overlapping hazards over the life of a facility. That reality changes how we should think about our designs, capital planning, and facility performance. Here's how we're going to move through today's presentation. We will begin with the changing wind threat environment, including why hurricanes and tornadoes can no longer be treated as completely separate planning risks. Then we will discuss storm shelters and what a building code requires, specifically and particularly through ICC 500. From there, we will focus on the gap between compliance and performance. We will look at the complex trap where assumptions about material strength or code compliance can create a false sense of security. Then we will discuss what resilience actually looks like, including passive and active strategies, assessment-based planning, and integrated design. Finally, we'll close with case studies, funding considerations, and practical takeaway for owners and project teams. Let's start with the broader hazard environment. For a long time, facility planning in many parts of the country followed a fairly simple mental model. Coastal areas planned for hurricanes. Central and plain states planned for tornadoes. Inland communities often thought of hurricanes as someone else's problem. That model is no longer accurate. Recent storm events have shown that hurricanes can produce destructive effects far outside the immediate landfall area, including tornadoes, inland flooding, and regional infrastructure disruptions. Recently, Florida experienced significant tornado activity in the 2024 associated wind events with Hurricane Milton and Helene, and that the first 3 months of 2026 produced roughly 274 confirmed tornadoes across the United States, one of the most active starts to a year on record. The video that you saw was a video taken by one of our WGI associates and structural engineer from his front porch in Palm Beach County, which is a region not generally considered a tornado risk. The key point is not simply that storms are happening. The key point is that facilities may be exposed to more than one type of wind hazard over its useful life. That means long-term facility planning cannot be based on the event type that has historically and most commonly been associated with that location. For owners, this changes the question from what hazard do we typically see here to what hazards could reasonably affect this facility during its life, and what level of performance do we expect when that happens. This map captures that issue visually. Florida, Texas, and North Carolina sit in regions where hurricane and tornado risk overlap. The white paper that we produced a few weeks back describes these areas as dual threat zones, where facilities can be exposed to both hurricane and tornado hazards over time. That matters because the design assumptions for one type of event may not fully address the demands associated with another. A facility designed for hurricane wind pressure is not automatically designed for tornado level demands. A building that performs acceptably in one event may not perform acceptably in another. The other thing I really want to emphasize is that this is not just a coastal issue. Hurricane Ian in 2022 produced tornadoes more than 100 miles away from the landfall, and Hurricane Helene in 2024 produced destructive inland impacts across multiple states. When we talk about resilience, we're not only talking about beachfront buildings, hospitals, or emergency operations centers. We're talking about distribution facilities, municipal buildings, utilities, schools, civic facilities, public safety buildings, and private sector facilities that communities rely on after storm events. To understand performance, we also need to understand severity. Tornadoes are classified using the enhanced Fujita scale, which ranges from an EF0 to an EF5. EF0 events are associated with wind speeds in the 65 to 85 mile an hour range, while an EF5 exceeds 200 miles per hour. EF3 tornadoes fall in the 136 to 165 mile an hour range, which is just exceeding what most code wind design is based off of. And most tornadoes, roughly 95%, fall within the EF0 to EF2 range. But the EF3 and stronger wind events are often responsible for the most severe building damage and life safety consequences. This matters because not all buildings are designed for the same wind demand. The conventional building designed to meet the building code is not necessarily designed to resist EF3 through EF5 tornadoes. That does not mean the design is deficient. It means the building was designed for a hazard level required by the applicable code, occupancy, location, and risk category. That is why performance expectations need to be clearly defined. If an owner assumes a facility will remain functional after an extreme event, but the design requirements only address minimum life safety issues, there is a discrepancy between expectation and design intent. This brings us to the real question. For many critical facilities, the question is no longer simply, does the building meet code? That is simply important, but it's not the only thing here. The more complete questions are, was the facility engineered for demands beyond the minimum thresholds? Can operations continue after the event? Are power and communications resilient? Will access remain available? And can staff continue performing their critical functions after an event? These are operational questions and not structural questions. A facility can be structurally intact, but still be offline. This is a distinction between a building that is built to survive and a facility that is built to last. We'll now shift from a hazard environment to the code framework. Storm shelters are one of the most important tools we have for protecting occupants during extreme wind events. But it's important to understand what storm shelter requirements are intended to do, and just as importantly, what they are not intended to do. The purpose of this section is not to pick apart the building code, but the code does what it's intended to do, which is a function as the legal minimum baseline for structural integrity and occupant safety and protection. The problem occurs when we expect the code to address operational performance issues that are outside of this scope. The ICC 500 and FEMA P361 establish minimum standards for the design and construction of storm shelters and safe rooms. In many regions, including several of WGI's key markets, certain facility types with designed high wind regions trigger storm shelter requirements. The requirements are specific. ICC storm shelters are designed for very high wind speeds, up to 250 miles an hour. They must address missile impact resistance, occupant protection, ventilation, shelter accessibility, and independent peer reviews before permitting. These are important, proven, life safety focused requirements. When a shelter is designed, constructed, and inspected properly, it becomes a protected space for occupants during the event. But the graphic on the slide is critical. On the left side, it shows what compliance protects. On the right side, what operational resilience requires. Compliance protects people during the event, but resilience protects operations after the event. Those are related, but not identical outcomes. This slide directly ties to that in the boundary of the code. Building codes establish minimum life safety requirements. They do not typically require sustained operational power, redundant communications, flood protection access routes, continuity of operational planning, or facility functionality after a storm. That sentence is important enough to repeat in a slightly different way. A facility can meet code, protect occupants, and still be unable to perform its prescribed function after an event. That is not a failure of the code. Again, it's a reflection of the code's purpose. If an owner needs a building to remain occupied and operational, that expectation must be clearly defined early. It must be translated into structural, architectural, civil, MEP, communication, and operational decisions. If it's not well defined, the project team may deliver a code compliant building that still does not meet the owner's actual post-storm needs. This is the difference between survival and performance. A compliant building may remain standing and still become unusable. Possible outcomes include emergency lighting without operational power, communication failures, flooded access roads, generator limitations, or staff being unable to sustain their services. The short version of this: compliance protects occupants, resilience protects the occupants and the facility operations. For many facilities, especially public safety facilities, utilities, emergency operations centers, transportation facilities, distribution centers, and similar buildings both matter. Now we'll talk about what I call the compliance trap. The compliance trap occurs when code compliance, material strength, or general appearance of robustness create an assumption that a building will perform beyond what is designed to resist. This is where some of the most significant misunderstandings occur. One of the most common misconceptions is that material strength equals unlimited resilience. People often assume that a concrete building, a masonry building, or a heavy structural steel building are automatically capable of resisting extreme wind events. But structural performance is not based on material type alone. It is based on prescribed loads, load paths, connections, detailing, envelope performance, and the specific design criteria applied to that facility. A concrete wall is not automatically tornado-proof. A heavy building is not automatically resilient. A code-compliant building is not automatically capable of providing operational recovery. And structural survival does not automatically mean continuity. This is why assumptions are dangerous. When owners, occupants, or even design teams assume performance that was never explicitly designed for, funded, or coordinated, the risk is hidden until the actual event exposes it. Let's take an example of the Edwardsville distribution facility. It's a difficult but important example. In December 2021, an EF3 tornado struck southern Illinois. It recorded wind speeds exceeding 150 miles an hour, and for a structure that's of this type, likely it was designed for a wind speed of 120 miles an hour. Part of the roof structure and connections to load-bearing wall panels failed. Portions of the exterior walls failed, and 6 employees were killed. The important point for today's discussion is that the building was not described as a deficient building. It was an industrial warehouse constructed with tilt-up concrete bearing walls and designed in accordance with the applicable code requirements of the time. An EF3 tornado with wind speeds in range of 136 to 165 miles an hour can impose demands that exceed those required for conventional warehouse construction. When those demands are exceeded, the building's design capacity, progressive roof failure, and loss of exterior panels is what occurs. The lesson is not that the code failed. The lesson is that the code compliance does not equal the extreme event performance. That distinction matters for owners of large warehouses, logistic facilities, industrial buildings, and other structures where the building may not comply with the code, but still house people, operations, inventory, or community critical functions during severe weather events. Let's also take example Hurricane Maria in Puerto Rico. This illustrates a related issue to infrastructure scale. Electrical generation assets largely remained intact, but transmission and distribution systems had limited redundancy and few alternate load paths. When primary components failed, the system could not redistribute demand, and the failures cascaded across the network. That created prolonged interruption in power delivery, affecting hospitals, water treatment facilities, and other critical structures. The lesson here is that operational failure does not always require structural collapse. A structure may remain standing, but if utilities, communication, fuel supply, access, or distribution systems fail, the facility or system may not be able to function. This is one reason resilience must be considered as a system issue and not a structural issue alone. When WGI evaluates facilities for resilience, the same categories of gaps appear repeatedly. First, the building envelope performance. Roofs, walls, doors, windows, louvers, and openings often control whether damage remains localized or becomes operationally disruptive. Second is backup power. Many emergency power systems are designed for life safety loads or shelter functions, and not a full operational demand. Third is communications. A facility may have power, but if service pathways, carrier routes, or upstream infrastructure fails, the building can become operationally isolated. Fourth is site access. If roads are overtopped, grading directs water towards entrances, or parking and service areas flood, the building may be structurally sound but unusable. The fifth is continuity planning. Staffing, decision authority, operational sequencing, and degraded mode procedures are not established by the building code. They must be planned for. For most resilient failures occur between and beyond structural survival. One of the most practical issues is timing. Resilience investments are almost always more efficiently when they're incorporated during initial design. Structural load pass, roof uplift resistance, impact rated openings, envelope continuity, protected equipment locations, site drainage, and access planning are all easier to address when the project is being designed. For a simple example, a storm-rated door may cost approximately $8,000 during the original design and construction, but can exceed $30,000 if it's looking to be retrofitted into an existing opening. And that takes into account the reinforcing of the jambs, the sill, and the head. That example illustrates a larger point. Designing to the minimum code standard does not eliminate resilient investment. In many cases, it simply postpones it. The cost may come back later as post-storm repairs, insurance-driven upgrades, retrofit projects, or extended downtime occur. The practical question for owners is not whether resilience costs money, because it does. The question is whether those investments are made deliberately during design, when operations are available, or retroactively after failure when disruption and cost are much higher. At this point, we talked about the hazard, the code, and the gap between compliance and performance. Now let's talk about what resiliency looks like in practice. Resilience is not one product, one specification, or one upgrade. It's a coordinated set of decisions across structure, envelope, site, building systems, and operations. A good resilience program starts with an assessment. The Palm Beach County Resilience Assessment that WGI performed was a really good and useful example. The structural team at WGI conducted a resilience assessment of the county-owned facilities portfolio that included schools, civic centers, university buildings, and water utility facilities. This is not simply a code compliance audit. A code compliance audit asks whether the facility meets the adopted code. The resilience assessment asks whether the facility can perform as it's intended during and after a significant storm event. Those are two completely different questions. The assessment focused on operational consequence, facility function, prioritize hardening strategies, and risk-based investment planning. That decision is important. A water treatment facility serving hundreds of thousands of residents carries a very different consequence of failure than an administration building, even if both have similar physical vulnerabilities. The assessment process helps owners prioritize limited capital dollars based on consequence and not just efficiency. This slide introduces a critical concept, passive and active strategies. Passive strategies are built into the structure, envelope, and site. These include low path continuity, roof uplift resistance, impact rated assemblies, hardened envelope systems, protected openings, site grading, stormwater management, and shelter construction where required. Active strategies involve systems, redundancy, and operations. These include backup generators, fuel storage, redundant communications, dual mechanical and electrical systems, continuity of operation plans, staff development procedures, and a shelter-in-place protocol. Both are necessary, but they behave differently. Passive measures define the physical limits of performance. These are the most effective when incorporated during design and construction. Active systems operate within those physical limits and can sometimes be phased or expanded over time. That is why sequencing matters. Active systems cannot compensate for roof failure. Backup power cannot restore flooded access. Communications cannot function reliably if service pathways are physically damaged. The practical takeaway: build resilience from the structure outward. Resilience failure rarely originate neatly within one discipline. They often appear at the boundary between disciplines. For an example, the generator may be properly sized for an electrical perspective, but it's vulnerable if the structure, enclosure, openings, or site grading around it are not designed to the same hazard. Site drainage may function according to design assumptions, but if access roads become impassable, the facility may not be usable. Communications equipment may remain powered, but if the pathway or service entries are damaged, the operations still may be disconnected. This is why integrated design matters. Civil, structural, architectural, and MEP decisions need to be coordinated around the same performance objective. At WGI, our integrated approach is valuable because it allows those boundary conditions to surface early while they're still design decisions instead of later when they become operational failures or retrofit projects. Not every facility that needs to remain operational is classified as an essential facility under the building code. Distribution centers, grocery stores, municipal support buildings, utility operations, and fuel infrastructure may not fall neatly into the most stringent of the design codes, but they are essential to community recovery and economic continuity. If those facilities lose power, access, communications, inventory, or operational functionality, recovery slows. That can affect emergency response, public services, supply chains, fuel availability, food distribution, and daily operations. The question is not only what is the code classification, the better question is what happens if this facility cannot function after a storm. When failure has significant public, operational, economic consequences, the design conversation should shift from minimum compliance to intended performance. The Spartanburg County Emergency Operations Center is a strong example of designing with continuity as the objective. When Spartanburg County planned its replacement emergency operations center, the performance expectations were very explicit. The facility needed to support 20 core staff during routine emergency conditions and scale to more than 100 personnel during major events without operational interruption. The alternate 911 center needed to activate based on a defined trigger. Backup power needed to support full operational load. Mechanical and communication systems required redundancy. Site drainage needed to maintain vehicle access under storm conditions. The facility opened in 2022, and on September 26, 2024, Hurricane Helene made landfall as a Category 4 storm, and its impact extended into the Carolinas. Within hours, staff expanded from 20 core personnel to more than 100. The alternate 911 center came online. The generators held, and Spartanburg County maintained storm recovery operations from that building for more than 3 weeks without a break in service. That outcome was not the result of decisions made during the storm. It came from decisions made years earlier during programming and design. This is the core message of the presentation. Facilities that perform under stress are not lucky, they're planned for. The Escambia Santa Rosa Regional Traffic Management Center in Pensacola, Florida is another example of integrated design and practice. WGI served as prime consultant for the 30,000 square foot regional facility adjacent to Escambia County's Emergency Operations Center. The scope included project management, architecture, structural engineering, mechanical, electrical, and plumbing engineering, and subsurface utility engineering. Because of Pensacola's Gulf storm exposure, the project was approached as an integrated operational system, not simply as a collection of code-compliant components. The structural system was designed for coastal wind exposure. Mechanical and electrical systems were specified with redundancy appropriate to the facility's role. Site access, circulation, and backup power infrastructures were coordinated with the adjacent EOC. The key point is that risk category 4 was treated as a starting point and not as a guarantee. Operational continuity depended on additional decisions, including generator placement and protection, envelope performance, access, and shared failure scenarios. This is what resiliency looks like when it's coordinated across the disciplines. We'll move on to funding, because that's usually an important question. Resiliency investments is ultimately a capital planning decision. It competes with every other need an owner, a county, a municipality, utility, or private organization has. The challenge is that resiliency often lacks urgency until after an event. After the storm, the need is obvious, but before the storm, it has to be justified. That is why the most effective resilience conversations are not based on fear. They're based on total cost of ownership, operational consequence, insurance implications, downtime, recovery cost, and a comparative cost of planned investment versus reactive repair. The insurance market increasingly rewards demonstrated resilience. In high-risk coastal regions, particularly Florida and Texas, carriers are pricing based on demonstrated performance rather than assumed compliance. Facilities with documented hardening assessments, verified envelope performance, proven generator capacity, and a continuity of operational planning can present a different risk profile than facilities that simply meet the code. That can affect insurability, premium positioning, recovery cost, and business continuity. For leadership teams, the business case is strongest when resilience is framed as a capital strategy, not a technical preference. It is about reducing operational risk, managing insurance expectations, protecting continuity, and making investments before options become limited. The most compelling question for leadership is often, what does downtime cost us? And what would we wish we would have done before the event occurred? This slide summarizes our key takeaways. First, code compliance is a starting point and not the finish line. Building codes establish minimum life safety standards. They do not define the full scope of operational performance. Second, storm risk is now extending beyond traditional assumptions. Hurricanes, tornadoes, inland flooding, and regional infrastructure disruption can affect facilities that may not have historically planned for those combined risks. Third, survival and operational performance are different outcomes. A building can stand and still be unusable. Fourth, resilience requires coordinated decisions across disciplines. Structural, civil, architectural, MEP, communications, and operational planning all need to align around the same performance objective. And finally, early investments cost less than retroactive recovery. The opportunity to influence outcomes is greatest before the next design, renovation, or capital planning decision. And this is where WGI can help. Owners often know that resilience matters, but they don't they may not know where to start. Our role is to help define what a facility needs to do, identify where current performance may fall short, and align decision or capital planning decisions with those operational expectations. That can include structural resilient assessments, architecture and envelope design, MEP redundancy planning, site and access evaluation, capital planning, implementation support, and cross-disciplinary coordination. The outcome we are trying to support is not simply a code-compliant building. The outcome is a facility positioned to perform when conditions are at their worst. The main point I hope you take away from today is the storm does not test what we intended. It tests what we actually designed, built, coordinated, funded, and planned. The code-compliant building may protect people during the event, and that is most essential, but operational resilience requires more. It requires clear performance expectations, coordinated design, protected systems, reliability access, backup power, communications, and continuity planning. Those decisions are most effective before the storm, before construction, before renovation, and before the next capital planning event is finalized. That is the window where owners still have control over cost, scope, and performance. That is what separates facilities that are built to survive from facilities that are built to last. For those of you who want to take a deeper dive, we prepared a white paper that supports this presentation, Built to Survive versus Built to Last. The QR code is on the screen if you'd like to take a photo. It extends on the topics that we discussed today, which include storm shelter requirements, the compliance versus performance gap, case studies, resiliency strategies, and funding considerations. I encourage you to download it, share it with your teams, and use it as a starting point for your conversations about your own facilities. I'd like to thank you for your time today. This topic sits at the intersection of engineering operations, risk management, and leadership, and I hope this presentation helps reframe the conversation from does this building meet code to will this facility perform the way we intended it to perform? And if you have any questions, you want to discuss your portfolio, capital planning efforts, I've provided my contact information on this webinar. I'm assuming also if you take a picture of the QR code and I can go back, just give everybody one more chance if you want to take a picture of it. My name is also on the white paper, and you can contact me there or reach out through our website. There's my email address. And at this time, I'll open it up for questions.
If anybody has any direct questions for Robbie, go ahead and drop them in the Q&A, and we'll get those shared. If you don't want to ask them right now, you got his email. We can reach out as well. Give a couple of seconds here for anyone to drop any questions in the Q&A. Also, keep in mind, we'll be sending out a follow-up email that has the link to the recording and all that good stuff as well by the end of this week, so stay tuned for that. Doesn't look like we have any queued up, Robbie, so I think we should give people some time back for their lunch here. Again, we appreciate everyone joining us and sticking it out and listening to Robbie. This was great. Robbie, we appreciate it.
Thank you, everybody. Appreciate the time.